Good afternoon, everyone. Thank you for joining for the talk. And again, thank you to the organizers for the invitation. The title of my talk is Probing Realistic Water 2D Material Interfaces via Combined Quantum and Classical Simulations. Now, in our group, we are very much interested in understanding two-dimensional materials and their interfaces. And of course, as we all know, these are layered materials, and because of the weak van der Waals forces that are operative between the layers of these materials, they can be exfoliated into very thin sheets where several interesting properties emerge, both on the electronic structure side, but also on the transport side in terms of transport on and through these 2D materials. Now, there are several 2D materials, of course. Graphene is the prototypical one, composed of a single layer of carbon atoms, and this is semi-metallic and homopolar. But then there's others, like, there's hexagonal boron nitride, where instead of just carbons in the single layer, every other atom is a nitrogen in blue color, and every other atom is a boron in cream color. So, and just by replacing all the carbons with alternate borons and nitrogens, you get an insulating material with a very large band gap. And of course, this is a heteropolar material. So you can think of the edges of these materials could have some sort of polarity because there would be boron and nitrogen atoms of different electronegativity therein. There's also semiconducting materials like molybdenum disulfide, which is really a material of bigger class known as transition metal dichalcogenides. And since then, of course, many more 2D materials like maxenes and phosphorine and so on have been synthesized. But in our group right now, our focus is on these three materials. Now, in terms of applications, we've long heard that because these materials are flexible, they can be used in solar cells and flexible ones at that, due to their optoelectronic properties. Due to the mechanical properties, they could be used in lightweight composites when they are combined with polymeric materials. And finally, the application that we are more interested in our group is that of membrane applications, wherein you can think of creating either nanoporous membranes, wherein these 2D sheets have pores, or you have lamellar membranes where these sheets are stacked on top of each other, and then these lamellae can be created, and transport of ions, molecules, and gases can be studied through these. And this is sort of the focus in the talk, wherein we want to understand the nanofluidic interface when you have water in contact with boron nitride. In our group, we sort of try to combine classical and quantum mechanical simulations for understanding thermodynamics and kinetics at the nanoscale. Density functional theory is a tool that we often use when trying to understand the catalytic activity or trying to predict reaction barriers or free energies. But sometimes we also use these barriers and free energies to estimate rates that we put together in a Monte Carlo simulation to understand more complex phenomena like chemical vapor deposition of 2D materials or nanopore formation inside 2D materials. The other way we try to use DFT is to train atomic force fields, and then trying to understand, by performing molecular dynamic simulations, phenomena like wetting, friction, colloidal interactions between 2D flakes, and so on. And a recent thrust in our group has been the use of physically motivated features to distill the performance of a material or of a nanopore into its properties through the use of machine learning, which could be useful in the prediction and discovery of materials for catalysis and separations. So with that background of what the group does, I'm now going to delve into the talk, which is focused on applications of boron nitride at interfaces. And like I said, this is an insulating and heteropolar 2D material consisting of alternate boron and nitrogen atoms in a hexagonal structure inside a single layer. Now, this is the example that I quoted earlier, and this is experimentally, it's been reported that you could actually do desalination of seawater using lamellar HBN membranes. The other applications that have been looked at are oil water separation. Here again, you would want to tune the interactions between water, oil, and the 2D material, and try to use that to separate hydrophilic and hydrophobic phases. And finally, in terms of some modeling work, this is work which is now almost a decade ago, wherein Angelos Michailidis looked at friction on boron nitride and graphene through ab initio molecular dynamic simulations, and they showed a threefold difference between the friction coefficients on boron nitride and graphene due to electronic structure effects. So far, what has been done, or what had been done in the literature, was to understand the water contact angle and slip length on pristine HBN without defects. So you carried out molecular dynamic simulations, tried to predict quantities like the contact angle, the slip length for a pristine surface. But then if you look at transmission electron microscopy images, small vacancy defects do prop up there, whether it's the nitrogen vacancy, boron vacancy, BN, B2N, and B3N vacancies, or even incompletely grown layers. So if you do a chemical vapor deposition synthesis, then the top layer may not be completely grown, and that may expose the edges, right? So the question was, can we incorporate these kind of defects into our modeling framework, right? So to do that, we considered two different concentrations of defects, a larger concentration and a smaller concentration. And of course, this is sort of limited by the size of the box that we can take. If we go too big, then there are problems in doing DFT calculations to obtain partial charges on the B and N atoms, right? So before we go into this, of course, the accuracy of any MD study depends on the force field that is used. And this was work that was done back in 2018, wherein we showed that by separating the intra and intersheet interactions, we could use ab initio molecular dynamics to fit the bond angle and dihedral parameters, and the non-bonded parameters could later be obtained by fitting to mechanical properties of HPN just by looking at the interlayer interactions. And once that was done, we were able to create a force field that was able to do reasonably well in 4 different ways to predict the intralayer and interlayer interaction, but also the phonon dispersion for the low energy acoustic modes and the water layer interactions. So what we did was the bonded parameters were obtained from ab initio MD, and the non-bonded Lennard-Jones parameters were fit to reproduce the crystal structure and the elastic constant C33. The other quantities, right, were predicted. So all these were fit, the ones shown in red, and the ones that were predicted, they are in reasonable agreement with each other, right? And a highlight of this particular work was when we looked at the water sheet interaction, and the dashed lines are the force field. This is the binding energy of water with the sheet as a function of distance. You could see that dispersion corrected DFT overbound water with the surface, but our force field lied very close to the Monte Carlo diffusion Monte Carlo results from the Michaelides group, right? So this was very good, and what this said is that we could use the TIP4P ice water model. That was the model used to get these cross interactions through combining rules, could be used in molecular dynamic studies. The other advantage of this TIP4P ice model, particularly for predicting the contact angle, we found that it can predict the surface tension of water in very good agreement with the experimental value, right? Now, the first thing to keep in mind is that defects lead to redistribution of charge inside the boron nitride layer. This is the interaction energy you can see. And for this, we did density functional theory calculations in the CP2K package. And we used a scheme known as density derived atomic point charges developed by Bloch, wherein Gaussians are used in the atomic sites to make the partial charges reproduce the moments of the charge of the actual charge distribution. And through this, you're able to reproduce the long range electrostatic potential of the material, right? And these, for example, is the set of partial charges on a sheet with the vacancy. And you can see that in the bulk, the charges are about plus minus 0.9. But you can see that here, close to the defect, of course, they're different. But even at the edge of the box, they have not quite regained their values in the bulk, which means that the defects are at such a high concentration that they are coupled with each other and the defects can see each other. So this is a very high defect concentration. When we looked at the lower concentration at the edge of the box, you are able to get the bulk charges of plus minus 0.9. Now, we checked the agreement between this is the electric potential versus the distance from the sheet. So we checked the DFT potential and the so-called MD potential, which really means just the potential due to the partial charges. And you could see that at a distance of about 3 angstroms from the sheet, which is at 7 angstroms, you can get good agreement between the DFT value and the partial charge based value. Now, why this 3 angstrom distance is important is because of course, closer than that, you have charge penetration effects, overlap of orbitals. You can't really reproduce what is going on there with partial charges. And the other thing is that the Lennard-Jones part of the potential on water really prevents water from coming closer to the sheet than 3 angstroms. So we are kind of good by just mapping the electric potential in this place and then matching that to the DFT data. And this was also done at the lower vacancy concentration, right? Now, what we found initially by plotting the water density profile as a function of the distance from the HBN layer was that the density profile is not significantly affected due to the presence of these different type of defects. And you can see that this is the first layer of water, the density of around 2.7 gram per centimeter cube, but of course, far away from the sheet, you regain the bulk water density profile. And this similar observation was made at both the vacancy concentrations, right? Now let's move on and try to understand slip on defective HBN. So what exactly is slip? What slip means is that the no slip boundary condition is violated at the nanoscale. So instead of the velocity of the liquid at the wall, at a stationary wall being 0, it is non-zero, and then you have to extrapolate the velocity profile to a distance b so that the velocity becomes 0. So the higher the slip length b, the higher slip, and the higher is the violation of the no slip condition, right? So the friction coefficient was estimated through a Green-Kubo relationship using the force that acts between the solid and the liquid, and the viscosity, of course, is given by the autocorrelation of the stress tensor, right? The shear stress tensor, right? Once this was done, we were able to get the slip length for different vacancy concentrations, right, for different defects. And the interesting thing is that compared to pristine HBN, the B vacancy, of course, has a lower slip length, but the N vacancy has a very high slip length compared to pristine HBN, right? But when you went to the lower sort of concentration, you get a very low slip length. So that means that when the defects are at sufficiently high concentrations, the defects are electrostatically coupled. And what that means is that the charges, right, are low, and this leads to a lowering of this slip length. So this was a very interesting finding, and the same observation was also made on the Stone-Wales defect. Now for a boron vacancy, the slip length is very low, and that's because the charges on the boron vacancy are very high, right? So you see that at a higher vacancy concentration, the slip increases. Like I said, the charges are attenuated, but then when you go to a lower concentration, the slip comes back to its pristine value, right? So the slip length on HBN with the N vacancy of Stone-Wales defect is comparable to that on graphene. So this is sort of comparable to graphene at sufficiently high defect concentrations, right? So that is what we saw. And then we went deeper. We saw the role of electrostatics by computing the friction coefficient due to only LJ interactions and looked at the electrostatic contribution. Now this contribution came out to 90% for the boron vacancy, but only 40% for the nitrogen vacancy. And we could also rationalize this based on the contour plots, right? So if you look at a B vacancy and an N vacancy and look at the contour plot, the electrostatic interaction energy is much higher here compared to the N vacancy, and then the LJ part is almost similar. So once you do the electrostatics plus LJ, of course, this part will be dominant, right? So the contribution of LJ to friction is similar, and then the electrostatics differentiates these two defects. And one interesting case study we did was, what if we use the bulk partial charges, and we chose the boron BN vacancy to test this because an equal number of B and N atoms are removed, which means the BN sheet will still be neutral if you assign the bulk charges. Now this is what happens when you use the DFT partial charges. You get a slip length of, you get a friction coefficient around 1.7 times 10 to the 5 Newton seconds per meter cube, but that becomes almost 3 times when you use the bulk partial charges. So if you do not consider charge redistribution inside the material, you will incorrectly predict a much higher friction coefficient, right? So that was all about the friction coefficient with vacancy defects, right? But we were also interested in understanding the contact angle, right, in the presence of defects, also roughness on the surface. So to simulate the contact angles, we use something known as the Young-Dupre equation, which states that the work of adhesion, which is the energy required, free energy required to separate water from the surface, is related to the contact angle theta as gamma, the surface tension, times 1 plus cosine of theta, right? And this work of adhesion is computed using free energy perturbation theory, wherein you convert the solid liquid interface to a vacuum liquid interface, and the energy that is free energy that is spent to convert the density profile looking like this to something like this, and turning off the interactions is the work of adhesion, right? So to do this, you scale the interaction energy between the water and the solid by interaction factor lambda. These are called soft core potentials and are implemented in the LAMMPS molecular simulation package, right? So once you did that, we were able to look at the effect of not only defects on the contact angle, but also roughness, right? So we considered an incompletely grown layer at the top of the sheet at two different concentrations. So if you convert the vacancy, instead of the vacancy concentration, we looked at the edge length per area, right? So that's why this is a length per area. And then there are two edges exposed because there's an edge on this side and there's an edge on that side, right? So these are the results for the contact angle as a function of the defect. And you can see that the edge defect has the largest effect at both the higher concentration and the lower concentration. But interestingly, at the lower concentration, if you look at the contact angle, the experimental value is very close to the value that we simulate in the presence of edges, right? So what this means is that surface roughness at low concentration leads to agreement with the experimental water contact angle. So that was very interesting. Then we also looked at the role of surface roughness in explaining the slip length, right? So if you computed the friction coefficient from the Green-Cobo relationship, these are the results for the slip length. So for pristine HBN, it's about 7 nanometers, like we discussed earlier, but with exposed edges at high concentrations, it can come down to as low as 1.8 nanometers. And if you considered only flow perpendicular to the zigzag edge, it's almost just 1 nanometer. And this is very strikingly close to the experimental value measured by Kirti et al. From Radha Boya's group. And this was very interesting that just by considering roughness, we could map the experimental slip length to the simulated one. And the sort of physical insight that we got here was that the presence of edges due to the role of electrostatic interactions not only affects layering, right? So you can see the layering in the presence of the edges and in the absence of edges, but also the radial distribution function between the ONH in water and the BNN at the edge, right? Or at the rim of the defects, right? So you can see interesting features that come up in the presence of edge, which is the red color in the radial distribution function, right? So with that, I'd like to conclude my talk. I think it's about 20 minutes. We developed a classical force field to model HBN interfacial applications. I showed that if we don't use DFT to predict the partial charges, you could overestimate the friction coefficient with the example of a BN defect. Then we discussed that defects, particularly at a high vacancy concentration, may reduce friction and promote slippage on the HBN surface for water molecules. And finally, we saw how the presence of surface roughness in HBN can be used to bring the contact angle and the slip length, the predictions of those two quantities in line with very recent experimental data. Right. With that, I'd like to acknowledge the funding sources, the students who did the work, Aniruddha Seal for the work on the vacancy defects and the effect on the slip length, and Ashutosh Verma for the effect of roughness on both the contact angle and the slip length. This is a photo of my group, and this is the IISc campus and aerial view. So if you're here, I'd be happy to get in touch with you and host you. Thank you for listening. And thank you to the organizers for the invitation.